All right, we're finally done with Chapter 5, all that quantum mechanics stuff. But the rest of chemistry builds on that. So now, the next chapter is on trends on the periodic table, which I'm going to skim over that real briefly just today, because I want to get into the last chapter we're going to cover, and that's bonding. And we really need to do bonding before the year's over, and we're running low on time. So we're going to skip Chapter 6. Other than today, I'm going to spend my 15 minutes or whatever to go through some things that you're going to need to know for the next chapter, just real briefly. Luckily, there's not much here we have to worry about. And then tomorrow we'll pick up with Chapter 7 and look at bonding. Now, on the periodic table, there are some general trends you should be aware of. First of all, you already know the electron configurations follow the trends. This whole column is S1, this whole column is S2. These are all P1, P2, P3, and so on, the D block over here. So you already know the periodic table is organized around the electron configurations. More grows out of that. More properties grow out of these electron configurations and the periodic table in general. So the first thing I want to look at here is what they call here atomic size, which I usually call atomic radius, how big the atom is. Now, when you look on the periodic table, notice as you go down a column, we're in level 1, then we're in level 2, then we're in level 3, 4, 5, 6, 7 down here at francium. So as you go to bigger levels, those levels are further from the nucleus, and so you get a bigger atom. So as a general trend, if you go down a column on the periodic table, the size of the atom will get bigger. So hydrogen up here is a certain size. Lithium below it is bigger. Sodium below that is even bigger yet, and so on. So the biggest one in this column is the one at the bottom, which is francium. That holds true for all columns. So if I go over here to the halogen column, fluorine's the smallest, chlorine's bigger, bromine's bigger yet, iodine's even bigger, and astatine is huge. All right, so they get bigger going down the columns. You may find some rare exceptions here and there, but this trend holds true pretty well. Now, the other big trend with size is as you go across the periodic table, the atoms get a little smaller. Now, that's hard to see sometimes because you think about it, we're going from lithium with 3 electrons to beryllium with 4, boron with 5, and so on. We're adding electrons. So why wouldn't that electron cloud get bigger as you add them? Well, the reason is we're adding to the same level. The electron in lithium here is in level 2, 2s1. You go to beryllium, yes, you added another electron, but it's still in level 2. It's 2s2. Boron over here, 2p1. Yeah, it's a P instead of an S, but it's still in level 2. And everything in level 2 is about the same size, give or take. So, as you go across a row, you're going in the same level, so it's not going to get bigger. So then you're going to say, well, it'll stay the same size then, right? Well, in reality, it actually shrinks a little. And here's the reason why. Yeah, you're in level 2, but lithium here has 3 protons in the nucleus pulling on level 2. Beryllium has 4 protons pulling on level 2, so it pulls it in tighter. Boron has 5 protons in the nucleus pulling on level 2, so it pulls it in even tighter yet. The term we use for that is nuclear force, or really effective nuclear force. As you go across a row, the nucleus is applying a greater and greater force on those electrons. And so even though you're staying in the same row, the same shell, level 2, it's being pulled in by a stronger and stronger force, so that level 2 shell shrinks smaller and smaller as you go across. Why doesn't that happen going down as well? Well, I guess each individual shell does shrink as you go down, but you're adding new layers as you go. So layer 1, energy level 1 in hydrogen is a certain size. In lithium, level 1 is smaller, sure, but now we're in level 2. And level 2 is always going to be bigger than level 1. You go down here to sodium, yeah, levels 1 and 2 have shrunk, but now we're in level 3, and that's bigger than all the others. So as you go down a column, you get bigger because you're adding new levels, and those new levels are huge compared to the previous levels no matter what. As you go across, you're not adding new levels, so you're staying the same at best, but since the nucleus is getting stronger, those levels are being pulled tighter and tighter, and so the size gets smaller. So, going across the second row, lithium is the biggest. All the way over here, the noble gas at the end, neon, is going to be the smallest. We usually ignore the noble gases because they don't react with anything, and we're going to care about this because it affects the way they react. So the smallest atom we usually have to worry about is fluorine over here. Okay? Notice as you go across, they get smaller, so something on the right is going to be the smallest. As you go down, they get bigger, so at the top must be the smallest. Fluorine right here is the smallest atom that is going to be involved in reactions. Yeah, helium up here is tiny too, but who cares? It never reacts with anything. The biggest atom on the periodic table, well, they get bigger going down, so someone at the bottom is the biggest. And of course, they get smaller going across, so coming back to the left, francium in the lower left corner is the biggest atom of them all. Okay, so francium's a huge giant over here. Fluorine is a tiny little atom over there. And that's going to affect what they do. Now, why does it affect what they do? Let me go to the next periodic table picture and talk about ionization. You don't have to worry about that graph. About ionization energy. Now, let's take an atom and try to rip an electron off of it. So I'm going to go in there, grab its outermost electron, that's the easiest one to get, and rip it out of the atom. Obviously, it's going to take some energy to do that because the nucleus is trying to hold on to its negative electrons. So, the energy it takes to do that is called ionization energy. Why? Because when you rip the electron out, it's now an ion. So, the ionization energy is how much energy it takes to rip an electron out of the atom. And it's a measure of really how strong the atom is attracting electrons. If it takes you a whole lot of energy, the atom must be holding onto it really tightly. If it doesn't take you much energy at all to rip an electron out of there, the atom isn't holding onto it real tightly and just goes away. So, as you go down a column, the ionization energy decreases. In other words, it gets easier and easier to rip electrons out of the atom as you go down a column. Hydrogen holds onto its electron pretty tightly. As you go down, it gets easier and easier, less force needed, less energy needed. By the time you get down here to francium, it's wimpy. Its electrons are so far from the nucleus, you can easily rip them off of it. Okay? So just like in the real world, France surrenders quite easily, right? So down as you go down a column, ionization energy decreases. It gets easier and easier to rip electrons free, which means they're more likely to form positive ions. If you can easily pull an electron off of francium here, it's going to form a positive ion just like that. If it takes work, a little more work to take an electron off of hydrogen up here, it's going to be harder to make it form a positive ion. Okay? As you go across a row, for similar reasons before, the ionization energy gets higher. Why? Because the atom is shrinking. So the electrons are getting pulled closer to the nucleus. They're being held more tightly. It's harder to rip them free. Okay? So going across the second row, lithium over here is the biggest in that row, so its electrons are loosely held and it's easy to rip electrons off of it. It forms positive charges quite readily. As you go across over here to fluorine, it's the smallest of them all, so it's holding onto its electrons real tightly, and it's very, very difficult to remove electrons from it. Okay? Think of a big atom as you walking down the halls, when we're allowed to be in the halls anyway, wear your mask, walking down the halls with your books held out at arm's length. You know, holding them in your hands at the end of your arms, just waving them out in the air like that. Some bully's going to come along and smack them out of your hands. Probably going to be me. But it's not going to take much energy for them to do that because you're holding them so far away from your body and so loosely in your hands. So a big atom down here at the bottom left of the periodic table is like that. It's easy to smack the electrons out of the atom. It takes little energy to do it. On the other hand, up here in the upper right, like fluorine and the elements near it, they're holding their books tight in by their chest. And so if the bully wants to rip the books out of their hands, they're going to have to use a lot of energy to do it. They're going to have to force them out of there. And I don't want to do that much work. So therefore, it's very, very hard to rip electrons out of these atoms over here. And therefore, they don't form positive ions. In fact, they go the other way. They take other people's electrons and form negative ions. So remember early in the year, we talked about metals are metals because they form positive ions. Nonmetals are what they are because they form negative ions. Now we can see why. Atoms get bigger as you go down toward this left-hand corner. Bigger means easier to lose electrons, And so elements over in the lower left here are going to be metals. As you move toward the upper right, the atoms get smaller and smaller and hold their electrons tighter and tighter, until eventually you reach a point where you can't remove them from the electron. You can't remove electrons from the atom anymore, and they cease being metals. Now you got your metalloids in there where they're kind of, they can't gain, they can't lose, whatever. You continue to go to the upper right, and the atoms are now so small that they hold their electrons so tightly they actually grab other people's electrons, and they gain electrons, and they're nonmetals. So we've known all year long that nonmetals are the elements in the upper right corner, and metals are the rest of the periodic table. Now we got a good indication of why. It comes back to the sizes of the atoms and how it relates to the energy it takes to rip electrons free. Now, one last term I want to talk about is electronegativity. Okay? Notice we've been talking about how well we attract electrons, and we've been measuring it by ripping electrons out of the atom, or feeding it to the atom if you want to go the opposite way, which they do, and you don't have to worry about that. But what if you want to form a covalent bond and share electrons? Now nobody's gaining, nobody's losing. Now, how well they share electrons is going to depend still on how strongly they're attracting. But you can't use ionization energy because no one's getting ionized. So we invent a whole new word. We call it electronegativity. And it measures the same exact thing, how well we're attracting electrons. But now it's measuring it in a shared pair of electrons in a covalent bond. But it follows the same trend. Electronegativity gets smaller as you go down a column because the atoms are getting bigger and they're not going to hold electrons real well, so they're not going to share real easily. It gets bigger going across, they're going to pull the electrons more tightly to themselves. So again, in the upper right, they're not going to share real easily. If their electronegativities are similar enough, then they're both pulling with similar strength and they'll share electrons and form covalent bonds. So electronegativity follows the same trend you see here. It's measuring how well they share, or how strongly they pull on those shared electrons. Fluorine up here pulls real strongly. It's got a large electronegativity. So if you build a covalent bond with fluorine in there, fluorine's going to pull those electrons real hard toward itself. And maybe it won't even share evenly. It'll share unequally because it's greedy. You put a wimpier atom over in here in your molecule, and it may try to share more equally because it doesn't have a real strong attraction. You put a real wimpy atom, like over here by francium in the molecule, try to share electrons with it. It's so wimpy, everyone can rip the electrons out of its hands. It's like, me being so much stronger than all the rest of you. If we had a tug of war, I'd just rip the rope out of your hands. Okay, you guys are like francium. I'm like fluorine, right? At least we can let me believe that. Anyway, just last thing I wanted to kind of show you on this slideshow. I'm going to skip this stuff because it's not terribly important. How to spell electronegativity. There it is. So I've been using the word. It's a big, ugly, scary chemistry word. But again now, if we look at an abbreviated periodic table, notice they cut out the transition metals in the middle to squish it together. They show all the trends together here. Some of these we don't have to worry about. So again, notice as you go down a column, the atom gets bigger. And therefore, the ionization energy and the electron affinity, which are both measuring attraction, gets smaller. Size gets bigger, attraction gets smaller. We measure that attraction by forming ionic bonds with ionization energy. We measure that attraction forming covalent bonds using electronegativity. As you go across a row, the size gets smaller, decreases, therefore the attraction gets larger. And so the ionization energy and the electronegativity will both increase going across a row. Again, there's all kinds of other factors involved here, and so these trends don't always hold true. You're going to find all kinds of flaws and exceptions in this. But the general overall trends hold true. And understanding these trends, which atoms are bigger than which ones have stronger attraction than which, understanding this will allow us to understand how atoms bond in certain ways with each other. Why do sodium and chlorine form ionic bonds versus carbon and hydrogen form covalent bonds? Instead, they share. The reason for all that has to do with these relative attraction forces. But again, I didn't want to go through this whole chapter because we don't have time for it. I just wanted to give you kind of these few things that are important in the chapter that are going to be used in the bonding chapter. So tomorrow we'll go on and we'll start talking about bonding. And I am done for the day.